We've looked a lot at Punnett squares, but another important tool used in looking at genetics is pedigrees. Now, pedigrees are charts that show traits and how they're distributed across families over generations. And you can use pedigrees to work backwards and determine the inheritance of a trait if you're looking for certain patterns. Now, there are typical ways to represent, not 100% of the time, but most of the time, the square is used to represent the male and the circle for the female. Affected means the phenotype is showing. Now, almost always these are for diseases. So an affected person would be a person who has the disease trait. And the generations are numbered in Roman numerals. So this would be the first generation, second generation, and third generation represented here. And this line means mating. So this number 2 and 3 in generation 2 are the children of this pairing. And so this means a mating pair. All right, so certain patterns. In a situation where the trait is autosomal recessive, you could see it skip a generation. So you're not likely to see that if it's not autosomal recessive, and it could show up and appear later. Also, males and females are affected equally. So let's play around with this a little bit. In the case of autosomal recessive, you know for sure that the genotype of these is this. Now, in order for all of these offspring in generation 2 to be non-affected, most likely this is the genotype of the father in this instance, which would make all of these heterozygous and unaffected, which is why you can see here, we really can't determine that. That wasn't an offspring. Sorry, I got a little carried away there. Now for this, if this is a heterozygote, for there to be some non-affected and one affected offspring, then this one has to also be a heterozygote. And then these could be, we could represent these this way, meaning they're either homozygous dominant or heterozygous. We don't really know which. So let's work through this again. This is another autosomal recessive example. So is this the same one I just did? It is. I already did this, but I'll write them down again. I forgot I had a slide for this already. And again, these could be either one of these two. It's really a 50% chance either way that these two are each of these. All right, in the case where it's autosomal dominant, normally do not skip generations. Again, unless it's sex-linked, you should see it affecting males and females relatively equally, and all of the unaffected members are homozygous recessive. So in this case, if it's autosomal dominant, then you know anyone unaffected is homozygous recessive. And this could be this. This one we know for sure is a heterozygote because one parent. Oh, I guess we know that one's a heterozygote too. And the reason I know that is because if this is affected and the trait is autosomal dominant, then there has to be at least one dominant allele, but there can only be one dominant allele because we know that the mother in this case is homozygous recessive. X-linked recessive. If it's X-linked, you're going to see a difference in affected males versus females. So in this instance, you've got 1, 2, 3 females, 1, 2, 3, 4, 5 males. So you've got 5 to 3 male to female ratio. So that's a good hint. And then the unaffected males would have to have the normal X allele. And so that's how this genotype setup was worked out. and that's an X-linked recessive. In X-linked dominant, again, you're going to see the trait in all individuals that have the dominant allele. So even though it is sex-linked, if it's X-linked dominant, it's just as likely to show up in females as it is in males, because even if females only have one allele for the trait, they're still going to be affected. So you're going to see a more equal distribution, and homozygous affected females are going to pass the trait to all of their offspring. Because whether it's a female or a male, if it's dominant, they're going to pass it to all of them. All right, so here's an example where we're given a pedigree, and then we are asked to work backwards to try to figure out what the characteristic is. Well, right off the bat, I see I've got a 4-to-1 or 4-to-2 ratio of males to females. I've got more unaffected than affected, so that makes me think perhaps it's recessive. So first, I'm going to try to see if maybe it is X-linked recessive. So if it's X-linked recessive, then that means you'd have to have this scenario. Now, I can already tell this isn't possible, because in this case, this male offspring would have had to have had a Y and an XA, which means that he would have to have been affected. So use process of elimination. And that's how you work through these. You use process of elimination. So my other option, I accidentally erased it, was that it's recessive. And I can already tell that that's not the case, but we will work through it anyway, because, again, this isn't possible, because this would have to be this. All right, well, I came up with the whole recessive X-linked thing because I had more affected than unaffected individuals and more males. But let me look at some other patterns here. It looks like right here, if it were X-linked dominant, or if it were just regular dominant, and these were both recessive, then this could happen. So now I'm looking at the possibility that it's autosomal, meaning regular, not sex-linked, dominant. All right, so let me work backwards from there. Oops. Oh, good grief. And that would mean these would both have to be heterozygous, because otherwise they couldn't have had a homozygous recessive. And then these could both be either one. This would have to be heterozygote in order to have a homozygous recessive. Remember, this would have to be here. So yes, autosomal dominant works. And you go through that process, and that's not incorrect. It's not incorrect if you don't get it right the first time. That's how you work a pedigree. You look for different possibilities, and then you try it out until you find something that works. All right, this isn't the same one. Let's try again. Got equal number of male and females. And 1, 2, 3, 4, 5, 6. Like a third of that first round of offspring, the second generation. Let's try autosomal recessive and see if that works. So if it's autosomal recessive, Now, in order to have autosomal recessive offspring, this would have to be a heterozygote. And again, here would have to be a heterozygote. And here. This could be either. And so could this. This would have to be a heterozygote. This would have to be a heterozygote. Yep, autosomal recessive works. So that one was the first one that I tried was correct. But again, that if you don't get it correct the first time, that doesn't mean you're not doing it correctly. That's just part of the process. All right, so that's some examples of pedigrees. We'll practice some more of those in the lab as well.